Tonight we're going to be looking at algebraic proofs. I'm really excited about this. I know that you've probably heard that they are hard, but we're going to do them a little differently this year, which I think will help a lot with that. And they really are neat if you can learn them the right way. So first of all, we need to define what exactly is a proof. Well, a proof is just showing beyond a doubt that something is true. And this is my own personal definition of what a proof is. I think it's a little more, it's easier to understand than the definition they give you in the book. It's just showing that something is true. Beyond a doubt, it is true. Okay? So what we'll be doing is proving geometric theorems. So for instance, proving vertical angles are congruent. All right? So we're showing beyond a shadow of a doubt that vertical angles have to be congruent for every case. Not for a specific case, but for every case. Okay? Before we get straight into proofs, I'm going to look at some properties. These are properties that you've seen before in algebra, but we're going to go over them again because we are starting with algebraic proofs and then we'll work our way up to geometric ones. So the first is the addition property. If you are given that x minus 5 equals 12, then you can conclude that x is 17. So to know that this is addition property, you have to see what's going on behind the scenes. How did they get to x equals 17? Well, they added 5 to each side. So that is addition property. Okay, they added 5. Next is the subtraction property. If we are given x plus 6 equals 15, we can conclude that x equals 9. So what do we do here? We subtracted 6 from each side. So since we're subtracting something, the property we used is subtraction property. Okay, fair enough. The next is the multiplication property. So here we have x over 5 equals negative 2, then x equals negative 10. Well, here, if we multiply 5 from each side, those would cancel and we'd be left with x equals negative 2 times 5. So x equals negative 10. So that is multiplication property. We are multiplying something to each side. The next one is division property. If you are given 2x equals 8, then x equals 4. So how did they get from 2x equals 8 to x equals 4? Well, they divided by half. Okay, they divided there by 2, so they can conclude that x is 4. Last one, substitution property. Okay, for this, if I know that 2x plus 2, or y equals 2x plus 2, and that x is 5, then I know that 2 times 5 plus 2 equals y. So here, I took out an x, I substituted 5. So that is substitution. Okay, anytime you take something out and put something else in, that is substitution property. All right, let's look at these, and these might seem a little silly right now, especially the first few, but we are going to use them a lot. So the first is the reflexive property. We are given 30, just 30, and then we can conclude that 30 equals itself. 30 equals 30. Now I know that sounds really funny and useless, but we will use this a lot, and if you watched the video before this, you saw that they used reflexive property for like segments and angles. So for instance, angle A equals angle A, or is congruent to angle A. We'll use that a lot. We'll use sides a lot. So side AB is congruent to side AB. That's another time we'll use reflexive property a lot. So we'll use that more in a geometric sense than in a numerical sense. The next is symmetric property. If we are given x equals 5, then I can conclude that, 5 equals x, then I can conclude that x equals 5. So I'm just switching the order something is written. That is symmetric. I just switch the order, everything stays the same. The next one is the transitive property. Okay, Transitive property says if y equals j, and j equals 13, then I can combine the first and the last and say that y must also equal 13. We'll use that one a bunch. The next is the distributive property. You know what distributive property is. It means that if I have something like this in parentheses, I can distribute the 3 to both terms and come up with 3x minus 27. All right, next we have simplification. Okay, this is just like when you are combining something, when you're doing 12 minus 12. I just simplify to say that y equals 0 because I know that 12 minus 12 is 0. So if you have to show that step, that is simplification. The next one is combining like terms. This is when you're combining variables. Anytime you're doing that, that's combining like terms. So here we know that 45x minus 20x is 25x. So that is combining like terms. All right. Okay, so that's it for our properties. What I want us to do now is look at these examples and see if we can figure out what property is happening. What property we're using here. So given 6x plus 2 equals 12, I can conclude that 6x equals 10. So what happened here to get to 6x equals 10? Well, they subtracted 2 from each side. So this would be subtraction property. Okay, let's look at number 2. If a equals r and r equals 60, then a equals 60. So it looks like I took a and then I took 60 and put them together. That is transitive property. Transitive. And you should try to guess along with me. If you can read ahead of me, do that and see if you can get it before I say it. The next one is number 3. If 3x minus 7x equals 20, then negative 4x equals 20. So what did I do here? Instead of writing 3x minus 7x, I wrote negative 4. So that is just combining like terms. Combining like terms. And your book calls it something funky, but it's just combining like terms. Okay? And the last one, number 4. Given that 4 times q minus x equals r, then 4q minus 4x equals r. So what did they do here? Well, they just distributed the 4 to each term. So that is distributive property. Okay. And the last one. Given that A is congruent to B, then angle B is congruent to angle A. So here they just switched the order they wrote something in, so that is symmetric. Symmetric. Okay, so now we're going to actually start looking at some proofs, which is exciting. The most common type of proof we'll use is the two-column proof. What the two-column proof has is it has a T-shape with statements being on your left side and reasons being on your right side. Okay, so you'll have a statement and then you'll give a reason for that statement. Okay, you'll have a next statement, then you'll give a reason for it. So like your first statement is usually whatever the problem gives you. So the first statement is usually your given, whatever that is. Okay, and your reason for that is that it was given in the problem. So then you'll move on to your second. You'll have some second statement, and then you'll give a reason for that statement. Okay, you'll have a third statement. You'll give a reason for that third statement. That is a two-column proof. So for every single statement you make, you have to have a reason for it. Okay, and until you get to what you're trying to prove. Okay, that is a two-column proof. Reasons can be different things. They can be properties, algebraic properties, the ones we just went over. They can be theorems that we've used before. So you can use theorems to prove other ones. They can be postulates we've used. They can be definitions of words that we've used before. They can also be given in the problem. So a reason can be a given. Okay, so those are all different things I want you to keep in mind when you're proving something that can be reasons. If they're not one of these, you're not going to be able to use it for a reason. So let's look at the following example. We aren't going to do a full proof. I just want to see if we can come up with our reason for this proof. So given that M is the midpoint of AC, what can you conclude? So what does it mean for M to be the midpoint? Well, it means it bisects the segment. So if it bisects the segment, what do we know about that diagram? What else can we say? Well, we can conclude that AM is congruent to MC. I know that these two segments have to be congruent. Now, what would your reason be for that? My reason would be what? Well, I know what it means to be a midpoint. If I know what it means to be a midpoint, then I know that AM is congruent to MC. That is just going to be the definition. That's not a theorem. That's not a postulate. That's just a definition of midpoint. And you're going to say what the definition is for. Okay, so you'll use that a lot in your reasoning. So let's go ahead and let's look at a proof. Let's see if we can dive in and do this thing. All right. Actually, let's start with this one. We're going to start with this proof. So remember, on the left side, I'm going to have my statements. And then I'm going to have my reasons. Dun, dun, dun. Okay. So our first statement is usually the given. So we are given that angle 1 equals the measure of angle 3. So the measure of angle 1 equals the measure of angle 3. And our reason for that would be given. Now, let's understand what we're trying to end up with. I eventually want to prove that the measure of those two angles are equal to one another. So angle AEC is here. Angle DEB is here. I want to prove that those two angles are the same. So this red angle and this green angle, I want to know that those have the same measure. So I'm going to have to use angle 2 somewhere within my proof. I need to use angle 2. So what do you know about angle 2? Well, the only thing we know is that the measure of angle 2 is equal to itself. What is that when something is equal to itself? Oops, I meant to put a 1 there. Well, that's just reflexive property. Okay, so by reflexive property, I know it's congruent to itself. Now let's look at the green angle. That green angle is angle 1 plus angle 2. So let's see, if I know that, I know angle 1 is congruent to 3. I know 2 is equal to itself. So 1 plus 2 represents angle AEC. So I can say that. I can say that the measure, for my third statement, the measure of angle 1 plus the measure of angle 2 equals, well, it's got to equal the measure of angle 2 plus the measure of angle 3, right? The measure of angle 3 plus the measure of angle 2. I know this because I already knew that those two were congruent. I'm just adding something to both sides. So because I'm adding something to both sides, that would be the addition property. I'm just adding something to both sides. Okay, that's the addition property. All right, so now I can replace this with what it's equal to. So what is angle 1 plus angle 2? Well, I know that the measure of angle 1 plus the measure of angle 2 is the measure of that green angle, which is angle AEC. And I also know that the measure of angle 3 plus the measure of angle 2 is the measure of angle DEB. Okay, now how did I know that? Well, the angle addition postulate. that tells me that I can add angles together. The angle addition postulate. Okay. Now, and I'm running out of room here, so I'm going to go ahead and I'm going to make another little T over here, and we're going to continue over here with number 5. So, now I have that the measure of angle 1 in step 3 plus the measure of angle 2 equals the measure of angle 3 plus the measure of angle 2. Then I came down to number 4 and said that 1 plus 2 equals AEC, and 3 plus 2 equals DEB. Sorry, I don't know why I put D there. DEB. Okay, so if I replace number 3 with AEC and I replace the second part of number 3 with DEB, I'll have what I'm trying to prove. So that's awesome. So now I can say that the measure of angle AEC is equal to the measure of angle DEB, which is what I was trying to prove. Why do I know that? Well, I'm just substituting things into number 3. I just took my equation in number 3 and subbed things into it. Okay, so that was a geometric proof. That's what they look like. What we're going to do tomorrow when you come in is we're going to do some proofs. Some will be algebraic, which are a lot easier. We'll do a few on the board together. Some are going to be geometric, which require a little bit more work, but they're not too bad once you get the hang of them, okay? So we're just going to practice, practice, practice. All right, so see you tomorrow.